Memory for facial expressions. The power of a smile. Shimamura, Ross, and Bennett. University of California, Berkeley. Faces with expressions happy, surprise, anger, fear were presented at the study. Memory for facial expressions was tested by presenting the same faces with neutral expressions and asking participants to determine the expression that had been displayed at study. In three experiments, happy expressions were remembered better than other expressions. The advantage of a happy face was observed even when faces were inverted, upside down, and even when salient perceptual features, such as broad green, was controlled across conditions. These findings are couched in terms of source monitoring, in which memory for facial expressions reflects encoding of the dispositional context of a prior event. Introduction. A smile, a frown, a surprised look. Such facial expressions convey powerful social emotional dispositions. Indeed, facial expressions often foreshadow, amplify, and even supersede verbal communication. Both psychological and neurocognitive findings suggest multiple processes involved in the reception, encoding, recognition, and elicitation of facial expressions. Moreover, ever since Darwin's treatise on emotional expressions, it has been recognized that facial expressions are to a substantial degree universal and common across cultures. With respect to the encoding of facial expressions, some findings suggest a greater impact of negative expressions, for example, anger or fear, as opposed to positive ones, for example, happy or perhaps surprise. For example, the so called face in the crowd effect suggests that angry faces are detected faster than happy faces when they are presented within an array of other faces. Also, negative expressions interfere when performance requires processing of facial characteristics unrelated to the expression. Such interference effects suggest that the attentional focus is directed to negative expressions, and as a result, the processing of other stimulus features is compromised. From a socio-biological perspective, the ability to recognize angry or threatening expressions would be highly advantageous, for survival could not depend on an animal's ability to encode and react to such displays. Positive expressions, such as happy or surprise, also convey information important for selection, such as kinship or a willingness to mate. Some studies have suggested a processing advantage for positive expressions over negative ones. Carita and Endo, 1995, showed that reaction time to judge whether a face was happy or sad was faster for happy faces. Such studies have generally used schematic drawings of faces, and the effect is reduced when actual photographs of faces are used. Thus, with respect to the relative impact of positive as opposed to negative expressions, some findings suggest an advantage for negative expressions, for example, the face in the crown effect, whereas other findings suggest an advantage for positive expressions, for example, the expression identification. Neurocognitive studies have explored brain regions active during face processing. In neuroimaging studies, the encoding of facial expressions can, to some degree, be dissociated from the encoding of facial identity. Facial recognition, for example, involves temporal occipital regions, such as the fusiform gyrus, whereas the encoding of facial expressions appears to recruit other areas, such as the amygdala, cingulate gyrus, insula, and prefrontal regions. With respect to valence, findings suggest that negative emotions are biased towards right hemisphere activity, whereas positive emotions are biased toward left hemisphere activity. In the present study, we explored memory for facial expressions. Consider, consider the following scenario. Several days after chatting with a gregarious person at a party, one happens to see that person reading a book in the library. How likely is it that one will remember that person's prior emotional disposition? Would one remember that person's disposition better if it had been angry rather than happy? From this perspective, memory for facial expressions represent the encoding of one aspect of the social context of a prior episode. As such, facial expressions can be construed as source information. The source monitoring framework proposed by Johnson et al. 1993 states that source refers to conditions under which a memory is acquired, for example, the spatial, temporal, and social context of the event, the media and modalities through which it was perceived. Despite the many memory studies on face recognition, few studies have focused specifically on memory for facial expressions. That is, most studies of face recognition consider the discrimination of previously presented faces from new faces. Unlike such studies of face discrimination, the present study focuses on facial expression as an aspect of emotional source information. One study has assessed this phenomena within the context of a standard face recognition test. Black and white photographs of faces with either happy or angry expressions were presented at study. At test, neutral faces were presented, and the participants were given tests of identity recognition, for instance, old new discrimination. If the subjects judged a face as old, they were asked to report which expression it displayed at study, for instance, memory for facial expression. Although old new discrimination was better for happy faces than for angry faces, no difference was observed in source memory for the expressions themselves. To what degree are different facial expressions remembered? We addressed this issue by presenting study faces with various expressions: happy, surprise, anger, fear. At test, participants were shown neutral versions of previously presented faces, and they were asked to determine the expressions displayed at study. We were also interested in the role of facial properties, such as configural aspects of faces, in determining the degree to which facial expressions are remembered. Previous studies concerning the encoding of facial expressions are equivocal with respect to the relative advantage of positive and negative expressions. Some studies suggest an attentional benefit for angry expressions. Other studies suggest that happy expressions are identified faster. It is uncertain to what degree either attentional demands or ease of encoding determines how well an expression is remembered. Given the sociobiological significance of negative displays of emotion, anger, fear, one might expect these expressions to be remembered best. Experiment 1. Method. Participants: 28 undergraduate students, 7 men and 21 women, from the University of California, Berkeley, volunteered for the study and received course credit for their participation. The participants averaged 20.4 years of age and had an average of 15.4 years of education. On the basis of voluntary ethnic identification, 50% were Asian, 35.7% were Caucasian, and 14.3% identified themselves as other. Stimuli and apparatus. Color photographs of faces with emotional expressions were obtained from the Japanese and Caucasian facial expressions of emotion, a set developed by Matsumoto and Ekman, 1988. From this collection, we selected 32 faces, each of which displayed one of four expressions: happy, surprise, anger, fear. 8 faces per expression. Sample faces are shown in Figure 1. The faces were divided into two sets of 16 faces, half Caucasian, half Asian, half male, half female, with facial expressions distributed evenly across the two sets, four faces per expression. From the accompanying collection of neutral faces, we use as test items photographs of each of the 32 Japanese and Caucasian neutral faces database faces, but with neutral expressions. In addition, we used 18 other neutral faces from the J, A, C, No, F, of which 4 were used as neutral faces at study, 8 were used as new item tests, and 6 were used as buffers during the study phase to reduce primacy and recency effects. The stimuli for both study and test phases were presented using ePrime software on an IBM compatible computer. Procedure: in the study phase, participants were shown 20 faces, which included one set of 16 faces with emotional expressions: 4 happy, 4 surprise, 4 anger, 4 fear, and 4 faces with neutral expressions. Each face was shown for 3 seconds, and participants were instructed to determine the gender of each face by making a key press response. No mention was given of a subsequent memory test, and thus, the learning of facial expressions occurred in an incidental manner. The faces were presented in a random order to reduce primacy and recency effects. 3 neutral faces were presented at the beginning of the set, and 3 neutral faces were presented at the end of the set. Following the presentation of all faces, the procedure was repeated in the same manner so that participants were given 2 trials of the gender decision task for each face. Half the participants were given one set of 16 JACFEE faces for study, and the other half were given a different set of JACFEE faces. The JACFEE collection has been designed and coded according to a highly reliable and well studied set of criteria for displays of facial expressions. It should be noted, however, that the set includes only one emotional expression for each face, so that one cannot counterbalance specific faces across expressions. In the present study, the use of 2 different sets of faces served as a replication test to ensure that any observed effects were attributable to facial expressions rather than to extraneous item effects of specific faces. Immediately following the study phase, participants were shown neutral versions of the 20 study faces intermixed with 8 new neutral faces. A test stimulus consisted of a neutral face with 6 possible choices: happy, surprise, anger, fear, neutral, and new. Participants were asked to make key press responses to indicate the expression that a face displayed when it was presented during the gender decision task, or to indicate new if the face had not been presented previously. Participants were instructed to guess if they did not remember the facial expression. The test phase was self paced. Results and discussion. We first analyze overall old new recognition performance across the 5 facial expression conditions: happy, surprise, anger, fear, and neutral. Since performance was based on a 6 alternative forced choice test, we defined an old response as a study item not identified as new. For instance, identifying an item as old without regard to which facial expression was selected. There was a significant effect of facial expression on all new recognition. In planned comparisons, neutral faces were remembered better than happy, angry, or surprise expressions, whereas fear expressions were intermediate and not significantly different from the other expressions. These findings reflect the general benefit of viewing exactly the same neutral face at study and test. There was no difference in performance between the 2 study sets, which were composed of different faces. We were particularly interested in memory for facial expressions of previously presented faces. We calculated for each condition, the proportion of correctly identified expressions conditionalized on having identified a face as old. There was a significant effect across conditions. As is shown in Figure 2, neutral and happy expressions were remembered better than angry, fear, or surprise expressions. Indeed, memory performance for angry, fearful, and surprised hovered near chance performance. The difference between happy and neutral expressions did not reach significance. The findings could not be attributed to response biases because false alarms, error rates across facial expressions were comparable, except for a slight bias towards identifying new items as neutral. Moreover, we performed a D-line analysis to compare an individual's hit rate for each facial expression with the corresponding false alarm rate and found the same pattern of results. To prevent out the range values in the D-line calculation, scores of 1.0 were assigned 0.99 and scores of 0 were assigned 0.01. Specifically, there was an overall difference in D-line measures across the five facial expressions, with happy faces remembered better than all other except for neutral. Finally, the findings cannot be attributed to the specific faces used, for there was no difference between the two face sets. Experiment 2. Rather surprisingly, participants remembered a happy expression of a previously presented face better than an angry, surprised, or fearful expression. These findings appear contrary to those of studies in which angry or sad faces have been detected more readily and thus have attracted greater attention than happy faces have. However, the findings are consistent with those of studies in which happy faces have been identified or recognized faster than angry/sad faces. A well studied aspect of faces is that they have both configural components. For example, head shape, spatial relation of parts, and featural components, eyes, nose, mouth. One way to assess the role of configural and featural components is to use inverted, for instance, upside down, faces, which tend to diminish configural properties. Face inversion has been studied with respect to facial expressions. Interpretation of these inversion effects is mixed with respect to the degree to which expressions are based on holistic configural properties as opposed to more discrete featural properties. If the memory advantage for happy faces is attributed to configural properties, the effect should disappear when invert faces are used. In experiment 2, we use the same paradigm as in experiment 1, but the faces at both study and test were inverted. Method. Participants. 28 college undergraduates, 9 men and 19 women, were tested in this study and were given course credit for their participation. The participants averaged 19.3 years of age and 14.9 years of education. Their ethnic identification was 39.2% Asian, 46.4% Caucasian, and 14.2% other. Procedure. The design and procedure were identical to those of experiment 1, except for two changes. In the present experiment, all faces were rotated 180 degrees, upside down, at both study and test. Also, during the study phase, each face was presented for 4 seconds instead of 3 seconds as in experiment 1. In summary, 20 inverted faces, 4 happy, 4 surprised, 4 angry, 4 sad, and 4 neutral were presented at study in an incidental manner using a gender judgment test. At test, neutral versions of these faces were intermixed with 8 new neutral ones, and participants determined whether a test face had previously displayed a happy, surprised, angry, sad, or neutral expression during the gender decision test, or whether a test face was new. Results and discussion. Analysis of recognition performance for inverted faces revealed a significant effect across the five facial expression conditions. In planned comparisons, happy, angry, fear, and neutral faces were all better remembered than surprise faces. No other comparisons reached significance. There was no difference in performance between the two study sets. As is shown in Figure 3, memory for facial expressions of inverted faces revealed the same pattern of results that was found in Experiment 1. There was a significant effect of face expression memory across conditions, with neutral and happy expressions remembered better than angry, fear, or surprise expressions. The difference between happy and neutral expressions was not significant. False alarm rates across the facial expressions were comparable, except for a guessing bias to report new items as neutral. In a D-line analysis, we found the same pattern of results as that obtained for hit rates. Thus, differences in memory for facial expressions could not be attributed to differences in false alarm biases. There was no difference between the two sets of faces. Experiment 3. The benefit of a happy face persisted even when configural properties of faces were disrupted by presenting upside down faces. When compared with other facial expressions, a happy smile appears to be recognized easily, even for such inverted faces. In particular, the display of a broad grin with exposed teeth is quite distinctive, both in terms of perceptual and social qualities. In experiment 3, we attempted to disentangle the perceptual qualities of a broad grin from its social implications. Neutral faces were digitally altered by inserting a broad grin from another face onto the otherwise neutral expression. The grin was inserted in its correct orientation, suggesting a happy face, while the grin was inverted so that it was upside down with respect to the orientation of the rest of the face. As shown in Figure 4, inverted grins have the appearance of grimaces. These grimace faces are rather distinctive, perhaps even more distinctive than a truly smiling face. Importantly, both happy and grimace faces include the same broad grin, yet only one suggests a happy disposition. In the present experiment, memory was assessed for the expression of grimace and happy faces when the face were presented upside down. In this way, we could determine whether the benefit of a happy face persists even when the perceptual features are equated across conditions. Method. Participants. 32 college undergraduates, 14 men, 18 women, were tested in this experiment and were given course credit for their participation. Ethnic identification was 40.6% Asian, 37.5% Caucasian, and 22% other. Stimuli. Other than the stimuli used in this experiment, the design was nearly identical to that of experiment 2. In the present experiment, grins from the JACFEE set of happy faces were digitally superimposed onto 12 different neutral faces using Photoshop. For one set, the greens had the same orientation as the face. For another set with the same faces, the greens were inverted, rotated 180 degrees with respect to the face. These inverted greens had the appearance of a grimace. At the study, 6 of these faces were presented as happy faces, and the other 6 were presented as grimace faces. The faces in the happy and grimace conditions were counterbalanced across participants. At study, 24 inverted faces, 6 happy, 6 grimace, 6 fear, and 6 neutral, were presented in the gender judgment test, 4-second exposure. 3 additional neutral faces were presented at the beginning of the list, and 3 were presented at the end to reduce primacy and recency effects, respectively. Following presentation of the faces, the set was presented again for a second exposure. At test, neutral versions of these inverted faces were intermixed with 8 new neutral faces, and participants determined whether a test face had been displayed previously with a happy grimace fear or neutral expression during the gender decision task, or whether the test phase was new. Chance equals 20%. Results and discussion. Analysis revealed a significant effect across the four facial expression conditions. In planned comparisons, neutral expressions were remembered better than happy, grimace, and fear expressions. No other comparisons reached significance. As is shown in Figure 5, memory for facial expressions differed across conditions. Neutral expressions were remembered better than grimace or fear expression, but were not significantly different from happy expressions. Importantly, happy expressions were remembered better than grimace expressions, despite the fact that the only difference between these two conditions was the orientation of the smile with respect to the face. The difference between happy and fear expressions was not significant. False alarm rates across the facial responses were comparable across expressions, though somewhat biased towards neutral responses. In a D-line analysis, we found a similar pattern of results. General discussion. In three experiments, memory for facial expressions was assessed by presenting neutral faces and asking subjects to identify facial expressions displayed during the study phase. In this manner, we were interested in memory for an aspect of the social emotional context of a prior episode. Among the facial expressions tested, surprise, happy, fear, and anger, happy expressions were remembered best. The benefit of a smile occurred even when configural properties were disrupted, upside down faces, experiment 2. And even when faces were equated for the perceptual salience of a broad grin, happy versus grimace faces, experiment 3. One previous study has assessed memory for facial expression. Following presentation of angry and happy faces, participants viewed neutral faces at test and made old new recognition judgments. If a face was judged as old, they were asked to report whether the face had been presented as angry or happy. The authors found a benefit for happy faces on old new judgments, but not on angry versus happy source judgments. In the present study, we did not observe a reliable benefit for happy faces on derived measures of old new recognition. It should be noted, however, that hit rates were calculated from the source recognition scores so that old responses were based on the number of study items not given in response of new. In a recent analysis, recognition judgments were assessed in a paradigm similar to that used in the present study, but traditional old new recognition judgments were requested. Just as Dargenbow et al., we found a reliable benefit for happy expressions on old new judgments. Unlike Dargenbow et al. 2003, we observed better source memory for happy expressions than for other emotional expressions. We used incidental learning instructions, whereas Dargenbow et al. Used intentional learning instructions. Moreover, we compared happy expressions with several other expressions: surprise, fear, and anger. Finally, Dargenbow et al. Used two successive recognition responses to obtain measures of identity memory and memory for expressions. In the present study, we used one forced choice response, which is similar to the procedure in source memory tests. It may be that methodological differences between Dargenbow et al.'s study and ours determined the boundary conditions of this effect. For example, the particular set of expressions used or the method of testing. Our findings fit well with a source monitoring framework, in which an episode comprises many different components, including perceptual, conceptual, and dispositional features. Memory for a past episode, for instance, source memory, depends on the degree to which these components are processed during encoding. In the present study, facial expressions was viewed as part of the dispositional or emotional context of a prior experience. Our findings suggest that happy faces are processed more strongly than other emotionally laden expressions such as anger, fear, or surprise. Given previous findings suggesting that angry faces draw attentional resources more than happy faces do, it was somewhat surprising that happy expressions were remembered better than other expressions. One possibility is that angry faces draw attention to whatever has motivated the negative emotion rather than to the particular person who elicited the emotion. In other words, angry faces direct attention to the context or event that elicits anger. Why is the person angry at me? Whereas a smile directs attention to the particular person. For instance, source. Who elicits the smile? Who is the person smiling at me? To the extent that a smiling face communicates a social bond, familiarity, attractiveness, kinship, attention may be directed to the particular face eliciting the happy expression. These factors could determine the manner in which attention and memory are influenced by facial expressions. In any event, the present methods and findings offer a new direction in the analysis of facial expressions. Viewed from a source monitoring perspective, facial expressions are an aspect of the dispositional context within which an event is experienced. Issues of attentional focus and social emotional interpretations of expressions may determine the degree to which the effective quality of an event is remembered.